Hello everyone, thanks for sticking until the last session of the day. I will try to finish sooner so everybody can get to go home sooner. My name is Ujwala, I'm engineering manager at Uber. I'm leading a real-time analytics platform team, and my team is responsible for building the platform based on the Apache Pinot and Presto, which is catering to the analytical requirement of the many of the lines of businesses at Uber. So today, so this is a quick agenda for today's talk. I will initially start my talk with some of the real-time use cases at Uber, actually that are the critical business use cases. Then I will try to go over the brief architecture of RTA platform that is powered by Apache Pinot. Then the main content for this talk, which is the case study. So we migrated one of the use cases from Elasticsearch to Pinot, and while doing that, actually we had a great deal of learnings and also the great wins that I want to share with you today. And we will try to cover as many questions towards the end of this presentation. So again, some of you might have attended another talk by my colleague Liu Peng, which was in the morning time, and then he might have covered some of the similar slides. So there might be some overlap, but stay with me. So actually, we started using the Pinot at Uber around 2016 with a handful of use cases, and one of them you might be very well aware of, which is the restaurant manager use case. And that is the first part I'm going to talk about, which is the real-time and actionable insights. Because people wants to gain the insights from the data, but the more fresher the data is, you will be able to get the quicker insights, and then you can make some adjustments or you can take some actions which will help resolve certain conditions. So restaurant manager will gives you the quick overview of how your business is doing or how your restaurant is doing, how many orders that you had, or what are the missed orders, or what is the customers are saying about your restaurant. So this is the one way to get the more real-time insights about your business. The second type of use case for that we see at Uber is the time-sensitive decisions. So every minute there are X number of orders that are being created, and then there are Y number of couriers actually they are actually picking up the orders for you. If there is a misbalance, for example, there are large number of orders, but there are not enough couriers to pick up your order. That means it's not a good user experience, and they will not get their food in time. Again, but it's if you do the vice versa, let's say if there are handful of orders, but there are large number of couriers who are waiting to pick up the orders, so that means they are not getting enough business. So even if you have plenty of couriers on your platform, they might not make enough money. So it's again bad experience for the earners on the platform. So we want to maintain the healthy balance of the demand and supply, and then for doing that, actually we need to know what is the health of the marketplace in last few minutes, and then based on that you can adjust the something we call as a radius of delivery, delivery radius that you can adjust, and then control the demand and supply. And the third type of use case, that is the user engagement. So there are multiple apps that Uber supports, and one of the examples that I have given here is the Earner app, where earner who is a courier on the platform or maybe a driver on the platform, and then he wants to see that, okay, how much money he's making on the platform. And then just by providing this hourly earnings that they are making, we increase the user engagement with the apps. Similarly, there are other examples of ads, if you are showing the merchants that how much the ads are helping them to create a business, so they will be more inclined to invest into the ads for your on the Uber app. So these are the three high-level categories of the use cases that we see. But the crux of the whole thing is that, as you can see, there are three things that people are interested in. They want the access to their data at very fast. So that means we are looking at the very low latency applications. Then there is also the data freshness aspect to it, because the data they want to look at it should be more fresh and created in last few seconds to minute. And then they also want to do it at the scale. So like, because in the first case of the restaurant manager, there are like millions of merchants on the platform. So, your platform should scale for that count, like, so that cardinality. So considering all these requirements, like, we have built this real-time analytics platform using the Apache Pinot, and we have evolved it like over the last few years. And this is like somewhat the current state of the platform is. And as you can see, it's like not only about, just the Pinot, which is the core of it, but we have also built the ecosystem around that. So to start with, right, like, so Pinot supports both real-time and batch sources. On the real-time side, we try to ingest from, we ingest from Kafka. Then you also, some of the use cases use the Flink for the stream transformation, because sometimes you want to transform the data, process the data before you ingest into the Pinot. You want to do some kind of a pre-aggregations to reduce the footprint into the Pinot. So like, that is your real-time pipeline. On the batch side, actually, we also support ingesting the data from Hive tables. And then whether like it's a HDFS or Hive, like, then we provide an interface to set up these pipelines, ingestion pipelines into the Pinot. Again, all the users are not technically very strong who are trying to develop their solutions. So they might not know all the SQL constraints or maybe the data type or like the cardinality concepts of that, because Uber is mainly consisting of the ops people. So we want to make sure that the onboarding experience is also seamless for them. So we have heavily invested into the 3 kinds of onboarding layers. The one is like UI, which is our self-serve onboarding UI, where you can just, with a few clicks, you can set up the ingestion both from the Kafka as well as the Hive. CLI is more for like advanced users who know what they are trying to do, and then also they are more of a engineers or the data scientist. And then like third is the developer API, where because with the UI or the CLI, you still have to, you cannot create the large scale data sets in one go. So for them, we have made available the service APIs, where they can just create thousands of tables with just integrating with the service APIs. On the storage side, actually, we also have a layer for the metadata service. So what it does is like it has integration with other ecosystem components at Uber. To name a few, like data book, or like where user will be able to see the schemas of their table after the table is created. Like, so those kinds of integrations are made possible with the metadata service. And the core where all the magic happens, that is the Pinot. And on the query side, actually, we have the we are using the Presto, but we have greatly changed or modified it to make it like very optimal for the low latency queries, because as you might know, the Presto, what it does is like it tries to scan the data from the underlying data engine, and then it put it into the Presto clusters, and then try to run the queries efficiently. But in this case, you are like transferring the large amount of data over the network. So in the Neutrino, which is another variant of the Presto, what we have done is that we pushed the compute as much as possible to the storage, because Pinot is great at doing the aggregation. So you do not need the other way around. And it like drastically reduces your network bandwidth usage, and then also it can handle the thousands of QPS. So one of the use cases that we have at Uber is like more than 20,000 QPS, and we are still able to serve it like under like 100 millisecond P99. And then we have integrated this entire ecosystem with the internal BI tools. There are like very popular like query engines within the Uber. Then uGrafana, which like it is again the Grafana which is used at Uber, and then where we have created another plugin for the Neutrino within the uGrafana. So you will be able to write the Neutrino query, which are like just the Presto SQL queries, and you will be able to visualize your data in a different formats and different types of chart on the UI. Alerting, again, this is one of the most popular category of the use cases within Uber, like recently, where people don't want to just get the queries and their responses, but they also want to set up some alerts based on the data that they are getting. And then we have integrated this with the internal service called as a uMonitor, which essentially like runs the query at the frequency that you define, and then it takes some action, whether sending the PagerDuty alert or like maybe sending an email. The action should be defined by the user. And then there are like some custom UI. One of the example I'm going to talk about today is the health line. So that is also a custom UI, and then it internally makes queries to the Pinot or the neutrino. And the data sketches, this is like one of the new category of the use cases as well. Like there was a talk about the data sketch uses within the Uber yesterday. Again, like we were able to close the gap between the Druid and the Pinot by implementing like more efficient sketch functions family in the Pinot. So like this is kind of, this is the high level overview of the platform, but we also invested into some self-serve capabilities of the platform. So the first one, as I talked about, is the user onboarding. So with a few clicks, like you should be able to set up the workflows end to end. But the second is like actually discovery, like where I talked about where you will be able to go to some data book UI and then like search for your Pinot table, look at its schema, like set up some UDQ test on that, or to identify data freshness issues, or like maybe some count issues, ingestion issues, and etc. And the third is like the observability. Like as you grow the adoption of the Pinot, like within Uber, like we saw that there are like thousands of, like hundreds of users like who are going to use the platform, but we don't have hundreds of engineers to support them, right? Like so, more tools that we create for them to debug their own issues, like it reduces the contact with the Pinot support channel. So we like created, like added new features. For example, the query-based fingerprinting. Like, so user can track their query fingerprints and then see what is going on with that specific query shape. And then they can make some optimizations, like they can add the indexes. We also invested into the automated index generation tools. So based on your query shapes, like it will give you the recommendation of like what is the best index type for your queries, and then you can add it through the like UI, like the URQ UI, and then you should be able to reduce the query latency significantly. So that is the part of the self-serve observability. We also have created the monitoring at each level, so the, like Pinot broker, server controller, and then get more low-level insights for the data set. And then like last part is visualization, monitoring, and alerting. So that is the main integration tools. So when we started using the Pinot, we were like working with the individual teams, whether it's Uber Rides, Uber Ads, Uber Eats, or customer obsession. And then we used to work with them to onboard the individual use case. But later on, the adoption increased from just one use case to a platform integrations. So we started integrating with the U-metric platform, like from the Elasticsearch, or like there is another platform called as a Bullseye. And then these platforms were already using some other technology, right? And there were like multiple teams within Uber managing these technologies. So that means you are investing into the engineering resources. You are having a dedicated on-call for each of the service. Then you are also having you need to have some in-house expertise to debug the issues for that technology. So that means you really need to if there are like some like level 5 incidents, like you need to know that what is going on. You cannot just rely on the open source support, or maybe you cannot just rely on some third-party vendor to come in unless there is a like costly support contract, right? So what we did in the last 4 years is like we tried to consolidate like these technologies onto the Pinot as a single storage stack, and we have successfully deprecated AristDB, which was the GPU-based OLAP engine. It was developed at Uber, and it was like later on open sourced. But because of the cost efficiency, GPUs are like always expensive. And then we were able to build the feature set, which was missing in the Pinot at that time, and contributed back to the open source. For example, to deprecate the AristDB, we added like full upsert, like lookup join, geospatial indexes support, and deprecated that. And like similarly, we have been able to successfully consolidate the MemSQL, Elasticsearch use cases, and most recently the ClickHouse use cases onto the Pinot. So this is not only like reducing the cost to maintain a technology, but it is also possible because like the Pinot provides you this pluggable configuration support, or like the basic architecture to support the feature parity gap, right? Like that we are having with the technologies. And then we have been able to do like lot more with lot less because like it is now one single team managing the multiple use cases, but while doing that, we also increased our expertise within the Uber, and then like provide the better support and better reliability for these use cases. So one such use case, like which is the health line that I have highlighted here, that we migrated from Elasticsearch to Pinot, and then I'm going to talk about it in the detail. So what is this use case actually? Like, so let's know more about the health line, right? So actually, Uber has a multiple app family. So there are like various apps in Android and the Apple iOS for Uber Rides, Eats, Freight, Restaurant Manager. So that means it is a family of apps, and that you have to support for different regions, different languages, and different versions, right? So there is all these dimensions that you have to be aware of while you are providing some kind of monitoring on that. There are 11,000 changes that are rolled out. These are the either the config changes or the infra changes per week within Uber. So that means like when you are working at and like releasing the changes at such a speed, you also need to have the analytics on issues when they occur. So for example, if there are like some specific category, specific change that is like resulting into the large number of crashes for your service, and then that is affecting the reliability or like availability of the service, it has to be detected sooner. If you don't detect them in time, then it can result into a production rollouts with faulty changes. It will affect the user experience. It will like affect the transactions that are happening in the real time, and also they have a GB impact for the company. So, and overall, actually, this will reduce the trust of our customers on the platform, right? So that's why this is very crucial. And then, like, that's why we developed this like tool, which is the internal to the Uber, which is the main focus for it is like to avoid the potential outages and also reduce the large-scale user impact. So what it does is like it does everything. So it has like the crash logging. So every service at the Uber try to log the crash information or the exception information, and it also try to do the monitoring on top of it. It does run some analytical query on that, which is visualized through the Healthline UI. And then if there are like some issues, it also alerts the users. Like, so for example, if the service has a change which is causing the issue, then like it will create a ticket and assign it to the last person who made a code change for that repo. And then, and this is the analytics for all the Uber mobile apps and all the services. For example, there are like more than 6,000 services at Uber that we run at scale. So you can get the sense of like how what is the scale of this entire application. So this is a brief overview of how it looks. Again, this is just catered to one specific Uber app and then one specific version. So it is very the sample view of like what it does. So as you can see, there are like total number of sessions. So how many sessions it is creating per app. Then there is also like how many total users are actively using these apps like at a given point of time. So for example, here you can see the weekly data, but you can also do it at the more fine granular data like at hourly basis. It also shows like how many total fatal crashes are there. So the crash is essentially the fatal and non-fatal categories of issues, right? And then like it also try to bunch them together into or group them together into something called as an issue. So issue is basically the cluster of crashes, and then like which has some similar pattern. Fatal-free crash is the next metric, which is very, very crucial. For example, we roll out some experimental versions to the beta users, right? And then that's why you can see like some line like dropping below 100% for the fatal-free crash. So that means like the experiment is still open, and unless and until it doesn't reach like 100% fatal-free, we don't even release it to the public. So that's why these metrics are like really important. In the next, you will see the adoption rate. If you are releasing like some newer version, you will see the one graph going down, actually that means one of the version is being phased out and then other version is being rolled out. Like, so you can see the real-time monitoring of that. And then the last bottom, which is the crash modules, where you are looking at like the top modules which are like contributing to these crashes. And then you can slice and dice on individual module to see what is happening. Then you can also extract the individual exceptions and then also like take some preemptive actions to that. You can like relate it to some of the industry alternatives. Like for example, there is a Firebase, Sentry, and Bugsnag, which does the similar kind of reporting, like for the errors and exceptions and crashes. So Healthline is just the internal version of that. So actually, yeah, first of all, what is the motivation to even migrate it to the Elasticsearch, right? Like, so without understanding that, like we cannot even proceed further. So like there was a discussion about like phasing out the Elasticsearch at Uber, and then like, so that was the major contributor to this migration. But that was just one of the point. They were also running into some challenges on the Elasticsearch with respect to the reliability and the infra cost, high infra cost. So on the reliability side, actually, the cluster, they were constantly having the ingestion spikes, and when the ingestion is spiked, then they were not able to relay this information because the higher ingestion rate is the indication that like your crash data has increased. So you want to know like immediately what is going on, right? But like that was the time actually we used to have the reliability issues, and then we were not able to get the data in the real time. The second challenge was like because you are maintaining this entire ELK stash, like the ELK stack, right? Like which is composed of like Logstash, Elasticsearch, and Kibana, which we are maintaining some custom systems around it, and then like the infra costs are like really huge because of the data footprint, and that also leads to the on-call overhead. So the scale of this huge thing is like the session events is basically how many users are connecting with your app. Those are like around like 200K to 300K per second. Crash event like are always in like around 50, 60K per second. Like at peak, it can even go up to 80, 90K. Crash payload size, which is very interesting feature, and then I'm also going to talk about it in the next few slides, because it can vary from 10K to 500 KB, right? And then, but you still want to load this payload because when it is time to actually debug these issues, you want to like extract the actual crash and then look at the stack trace, right? Like, but if because this payload can be variable, it also affects like how we store the segments into the Pinot, and then that is like one of the challenges that we solved. So coming back to the data footprint, like it was around like 150, 160 terabytes on the Elasticsearch, and then I can talk about it, how much we were able to reduce it back. Understanding the use case is very, very important because when we start the migration for some of these use cases, the teams come up with like some assumptions, right? They think that, okay, this is the way that things work in Elasticsearch, then I should be able to map it one-to-one with the Pinot world, right? But that doesn't happen. We have to make use of the strengths of the Pinot to achieve the functionality. So always focus on the goals rather than the actual technology stack that they have currently. So this is a very high-level diagram about how the stack looked like. So there is a crash processing pipeline which is processing the crash events from all the Uber apps, or like maybe and they're essentially going through some service, and then like service is like logging all this information, and then crash processing pipeline is processing them, and then emitting into a Kafka topic. And that Kafka topic, again, like Logstash is similar, like you do some kind of a transformation and processing, and then put it into the Elasticsearch. There is a custom Healthline UI, and then Elasticsearch also supports the very sophisticated Kibana dashboard, right? And then Kibana has its own advantages. Like, so that was one of the major risks that was called out, okay, what will be the alternative in the Pinot, like Pinot world. And on the Pinot side, when we did the migration, actually, so your crash pipeline didn't change much. Your Kafka topic was the same. In the Flink, actually, we were able to do the transformation that users were like interested in, and then we were able to also do a lot of other optimizations like the compression, and also like we like sampled some of the stack traces and stored that into the byte format. Like, so all those we were able to do it into the Flink. And Here you can see also the Hive component, right? Because the Pinot supports the hybrid table, and we leverage that functionality to reduce the cost and also make sure that actually there are easier ways to backfill the historical data. And then so that's why there is a Hive component to it. Actually, we set it up as configured it as the hybrid table. And then we, as I showed in the first slide actually, so Ugrafana, which is integrated with the neutrino query service, we try to leverage that and then provide the similar experience that they had into the Grafana, that they had into the Kibana as a result. So let's go over some of the use cases that are served by Pinot for this Healthline UI. So this is the first one, counting the sessions users at various granularity, right? Whether it's a device, OS, and etc. So on the first, you can see the total sessions, total users. Those are kind of engagement metrics. So if there is a sudden decrease in the engagement metrics, so it indicates some issues. So that you have to triage. Then also the granularity of your data could be at minutes level, or maybe it could be at the days level or hourly level. So one of the things that we found out that for this specific portion of the Healthline use case, the data freshness didn't matter a lot. So even if you aggregate the data at let's say some minutes granularity, they were still able to convey the same information on the UI. So we changed our data modeling according to that. So for example, in this case, the goal was to count the distinct sessions per app, version, OS, and R. The table retention that they were asking was for 45 days. We use the Pinot hyperlog column type. So again, hyperlog is the approximation algorithm to do the counting on aggregation on the distinct counts, right? Then for the next thing that we did was you can have the separate roll-ups for each of the data. For example, for the real-time data, as this was configured as a hybrid table, for the real-time data, you can always have the 10-minute granularity and then our day level or hour level granularity for your offline data. So that way, actually, you will able to restrict the growth of the data and also provide the aggregation, the count distinct information for each of them. So the real-time table granularity with 10 minutes, actually the retention was 5 days, and then for offline table it was 45 days. I think for those who might not have a context on the hybrid table, so internally we create two tables, but when user try to query, it represents a single logical entity, and then offline, the query always honor the offline part if it is available, offline data. Otherwise, it will try to read it from the real-time table. So, and then merge the results together and then share it with the as a query response. Here you can see the overlap is around 4 to 5 days. So that was purposefully done to reduce the risks for the offline job failures, because for offline job we use something called as a piper, and if there are some job failures because of a number of reasons, you still have the real-time data to cover that. So that was important for the reliability point of view. And then for all types of these queries, we were able to get the latency less than 100 millisecond at P99. So next type actually, which is the counting crashes, right? So as on this UI, you can see, so this is another tab or the visualization that is provided by the same tool. And here you can see the crash, and then when the first instance of that crash was seen, and what is the most recent instance was seen, and what was the version, and what was the first and last version, right? So able to get a very granular information about a crash, and then these are the crashes, the type is crash, and then this is an individual issue. So that is basically a cluster of your crashes, right? We don't want to show individual line because it is the common category of the errors, or common category for the fatal or non-fatal errors. On the top, you can also see the summary about fatal-free sessions, total issue count, affected users by that rollout, and then we can, this information is very important so that you can really gauge the impact that it is going to have, and then also take some very quick actions based on the impact. So here actually for the Pinot point of view, it was just a simple group by, right? So this was very easy to support onto the Pinot compared to the Elasticsearch, because in the Elasticsearch you have kind of unstructured data while Pinot, it was perfect, and then you just run the like group by queries to get the different metrics here. So even, for example, for the basic aggregation, aggregation of crash metrics across the dimension, number of crashes per OS, version, distribution of the crashes, etc. We again went ahead with the hybrid table setup and then like applied the wide range of like indexes, like, and this is one of the most powerful feature of the Pinot, I believe. There are like lot of customization that you can do with the indexes, and then it drastically reduces your query latency latencies, which is a huge game changer. Active-active setup, like across 2 regions, this is again from the reliability point of view. So if one of the region goes down, you still have another copy of the data to serve from. And this is very, very crucial when you are doing some incident mitigation or like doing some planned maintenance, where you can fail over the traffic to the another region and then like start, like you can do the operations with a 0 downtime. So this specific setup actually, it was this was the specific category like where we saw the biggest improvement. We were able to reduce the ingestion lag from few minutes on the Elasticsearch to 10 seconds, and then also like 60% improved page load time. So this was the UI, right? Like so, and you are loading those many crashes at a given time. So those were in seconds on Elasticsearch, and we were able to get it below 300 milliseconds. Aggregation was in the complex field. For example, if you have a crash context, and the payload will have the some nested JSON, right? Because it will store some stack trace, like analytical events, some experimental tags like that we have to identify. So when we onboarded this use case, like the Pinot was on the lower version of the Apache Pinot. I think it was 0.11, and we had to go with the flattening schema, like where you explode the complex JSON into the key and values, right? But when we upgraded to the 0.12, like we could leverage the JSON indexing with a more advanced feature, where you can define this like depth of the JSON indexing, or like you can also exclude some arrays which are not going to be queried in your data sets. You can include or exclude some of the paths as well. So that helped us to significantly trim down on the data that you want to index. Next one is like handling large payload, right? Because the payloads are typically a few hundreds of KBs, and then like the segment size is, so actually 90% of the Pinot use cases where you do not have to do this tuning, but there are like still some advanced use cases where you have to look into the low level config and see that what makes sense for you. For example, in this case, like we can do the segment size based on the number of rows, like how many rows you are accumulating in the given segment, or you can also do it on the size based, right, like how much data you have in the segment. Or there is a third category where you can do it also based on the time, like after 24 hours, like you just flush the given segment or like seal the segment. And then here actually, because as the traffic was very spiky, if you go with the like heap size based, right, like then it will accumulate a lot number of segments, and it will try to commit them together. So that caused like some degradation, and also like impacted the query ingestion lag. So we did like multiple experiments, and we decided to go with the row based. So you define the row threshold for each of the segment, and based on that you will seal it. Again, we sampled the crashes. Like again, I don't want to go into deep into each of them, because there is I have linked the inch blog, which will go and talk about it in more granular details. But sample crash really helps us, where you do not have to ingest all the crashes into the Pinot. Like you can only sample few of them, and then like also use like the application level compression, like because you do the compression outside the Pinot, and then like the Pinot supports the byte column, where you will be able to store them more efficiently. And with that, like we were able to even handle the large like really large payloads where the stack traces are like 500 to 600 KBs. Text index, this was like the, now let's say you got to the UI, now you know actually what is the specific crash module that is like contributing to the large number of crashes. Now you want to go into the specifics of that. In most cases, like the customers want to search by the crash message or like exception or class name. So exception, class name, and like stack trace, like that is pretty common example, right? So these are the low QPS use case. It's not like everybody try to do the like text search, right? But you still have to support them with a reasonable SLA. And for that, we went ahead with the Pinot Lucene text index. It has like the standard analyzer where it tokenizes your entire stack trace by delimiters, and then like will return you based on the, like let's say if you try to search it with the some logger name or the class name, it will return you the data. If some customers have like some custom message that they are like embedding and then they want to search it by them, so in that case actually the standard analyzer doesn't help much. You need like more advanced analyzer. Our team has also contributed to some of them, and then like we plan to use them in the next versions of the Healthline. And there are like some issues that we had like to the segment not sealing, especially like there was limit on the, if your index goes beyond 2 GB, then it was not able to read the offset, because offset was set as the int and it was not really long. So for that we had to upgrade our forward index writer version, which Pinot also supports. It is provided by Pinot, so it's not, we didn't have to add that. And then we were able to make a lot more improvements on the text search queries. Coming back to the like, so yeah, I mean, we spent all this effort, but like what is the outcome, right? Because we want to, when we work on the migrations, right? So if you're just telling the customer team that, okay, we will be just changing the backend from system A to system B, if it is a lateral move, they're not that impressed, right? Because what is the additional value you are getting other than just changing the backend? So here we were able to demonstrate that. So first one, actually we reduced the time to mitigate, like time to detect for mobile app crashes significantly. Because here, when there is a surge in your ingestion, that means like there is definitely some issue. Elasticsearch used to have some bottlenecks, like it didn't give you the fresh data, and then like the queries used to time out and etc. But with the Pinot, we were able to resolve those issues with the fine-tuning your segment size. And this was the first easy to see win. Then with the better latencies, actually the page loads improved 60% compared to the Elasticsearch. Now you are able to load the Health UI more efficiently, Healthline UI. Then improved reliability, because reliability is, because if your platform is not reliable, nobody is going to use it. So tolerance to spike, quicker lag recovery, because the spikes are going to happen. It's not like you can control, but it's how you react to that spike, right? And how quick you recover. And the reduced query timeout, actually. So this was very visible, because in case of Elasticsearch, what it does is like it used to build the indexes on the weekly data, weekly indexes, right? So if let's say in a given week you are seeing the surge in the ingestion, then if your query is touching that specific index, they used to time out mostly. But because in the Pinot, we kind of like tuned our segments and made them like more uniform, the queries timeouts, like they reduced significantly. And last but not the least, which is like no data loss, because of the issues that I mentioned with Elasticsearch, there used to be some patches of time where we used to lose some of the records, and that caused like some issues as well. And the most highlighted part of it, like the infrastructural savings, right? So we were able to save like around 2 million compared to the Elasticsearch for the infrastructural cost. 80% reduction in the CPU cores compared to Elasticsearch, and this was a huge, because without this, the most of the cost for the Elasticsearch was coming from the log stash, right? Elasticsearch is good at doing a lot more things that your application may or may not need, right? And then, but at the end of the day, you still keep maintaining the entire stack, and then like the cost grows significantly as you onboard more use cases. And then last one is like the 60% reduction in the data footprint, because you are pre-aggregating a lot more into the Flink pipeline. You are sampling the data, and that reduces your overall footprint. So we were able to bring it like less than 50 terabyte compared to 160 terabyte or like more on the Elasticsearch. And last slide about the learnings. So understanding the use case, as I said, like it's very, very crucial, because they come up with a different mindset. For example, in this case, we reduced the requirement of upserts, because in this case we modeled the data in such a way, and we did the most of the deduplication in the pre-aggregation pipeline, so we didn't even have to use the upsert. But if they just go with the documentation or like their current requirement, they will definitely go with the upsert in the Pinot, and then upset in the Pinot has like some other issues, right? Like with the memory overhead and other things. So we kind of cut down on that requirement. Also, they propose the requirement for the join, but like with the by using the Pinot subquery and then like the ID set feature, actually we also didn't have to do the complex joins. The next one is the query optimizations, like and the performance tuning. So you cannot expect the users to write a perfect query because they might not have a background, like writing the great SQL queries, right? Or like they might be coming from the background from the relational databases where the queries change drastically. So we spent a lot of time in building this tool. We worked with the customer and then like to rewrite their queries, take advantage of the indexes, various indexes, and sometimes actually how you write the query also matters. For example, some filters will be applied before even using the indexed data. So you need to make sure that the queries are written correctly. So we have some tools, automated tools, to provide this recommendation. But at the end of the day, we still have to work with the customer to do some tuning. And the segment tuning, again, as I talked about, like this might not be needed for the 90% of the use cases, but now we are like crossing that territory and moving into the more advanced type of use cases. This is becoming kind of a new de facto. For example, we are migrating some of the logging use cases from ClickHouse to Pinot, and there also we do look at this low-level configs. Peer download for the sealed segment. Like so, the default download type in the Pinot is like read from the deep store, which is the HDFS. And HDFS times out like typically when the segment size are like really huge, especially like 2 GBs or 3 GBs, right? So we changed to like the peer download model for the seer segment. So you read it from your peer servers, rather than going to the deep store, which might not have the same SLA or than the compared to the Pinot infrastructure. Data skewness. So data skewness can come at both the times, right? Ingestion time as well as the query time. Make sure that when you partition your Kafka topic, it is uniformly distributing the data, right? Otherwise, you will end up into a situation where some hosts are like highly utilized and some of them are like underutilized. Like so, you will have this skew. On the query time also, as I said, like some filters lead to the high row scan, and then that may not be optimal for your low latency application queries. So you might have to do some fine tuning as well there. So yeah, those are the learnings. We have documented like so a blog on this, like there is Overinch blog. Please check out the link if you want to know more, because there is a very limited time and then I can cover some part of it. Like, so I try to focus on most of the pain points that we saw and how we resolved it. But if you have any questions, or please let me know and then I can take those up.
Thanks for the presentation. My question is on the use cases. Do you have any use case that is exposed to consumers, like on the mobile app that is powered by Pinot? Yes. If so, what is the query concurrencies that you expect from Pinot?
Okay, great question actually. So if you have Uber Eats app, you can go to the search tab, and then like if you click on the search, it shows you the most recent searches, the search terms that you try to search on the app in last 60 days. So that is powered by Pinot. So, and the concurrency for that is like really high. Even the peak QPS can go around like 1.5K or close to 2000 QPS. But because those queries are very fine tuned, for example, your query shape doesn't change, right? Like that is very constant, and then you are only changing it the user UID in that case to get the search term. So the query latencies are still less than 50 to 80 milliseconds for them. So you don't see any lag or anything, but that is one of the user facing features you can look at.